our next talk, the first talk in the afternoon, will be given by Professor Hantao from Cardiff University, and he'll be talking about saliency and quality assessment. Please.
Thank you very much for the introduction, and good afternoon, everyone. So today I'm going to talk about our work on salience-driven approaches for image and video quality assessment. So first of all, I will briefly touch upon our work in this area, and then I'm going to divert my talk to saliency modeling, and also, in the end of the talk, I'm going to, briefly talk about, a few projects we've been involved in recent days. So perhaps, after lunch break, and let's get some, serious work to do. And, I'm going to do an attention test, and, for everybody in this audience, right? So are you ready? Okay. So just look at this image, a few seconds. And now I'm going to move it away, and I'm gonna bring it back. So the question is, what has changed? Yes?
The lady in the middle.
Yes?
Covered her back.
Yes, indeed. Anything else you have discovered?
There might be a foot missing on the right,
Mm-hmm.
right side of the image.
Right.
I'm not sure, but I think there was a wall and now.
Mm-hmm. So actually, yeah, let me just show you, there are a few changes. So this happens very, very often in our daily lives. So when we interact with images, right, so our understanding, our interpretation, or sometimes decision makings highly depend on, where we look in those images, or, visual information in general. Let me just do one more thing with you. So this is it's very interesting video I'm going to show you, and perhaps I'm not sure how much you will be surprised after, so in the end of the video, but just have a go with that. Oh, so I don't have. Just let me. Perhaps I don't have the audio going on, but. Should be. Yeah, just let me do the speaker. Okay. Right.
To test just how much attention the attention-stealing design of the new Skoda Fabia actually steals, we left one parked on this ordinary road in West London. We wanted to see if its sharp crystalline shapes, bold lines, and lower, wider profile would attract the desired level of attention. Will the 17-inch black alloy wheels stop passers-by in their tracks? Will the angular headlights attract the attention of other road users? Will a crowd gather to check out its fresh, sporty look? Well, not quite. But did the attention-stealing design distract you from noticing that the entire street has been changing right before your very eyes? Don't believe us? Have another look. Did you spot the van changing to a taxi? How about the scooter changing to a pair of bicycles? Or the lady holding a pig? Let alone the fact that the entire street is now completely different. Didn't think so. So there we have it. Proof.
Yeah, I don't know how many of you have seen that gorilla at the top left corner. So I didn't see that, the first time when I saw, this video. Yeah, so that. Sorry, let me check. Right. So the point is, attention is important. Without attention, we can't even move around in the real world. So let me just bring up our research in general. So the research problem, and in general, we are interested in image quality assessment. So two things we want to do. And the first one is how human beings understand and evaluate image quality, and second, how we can enable machines to do the same thing. So I presume most of you are familiar with image quality assessment, especially this emerging area in image processing, computer vision. But just let me very briefly go through so some of the a little bit background in this area. So if you are given this picture, right? So if you are asked to evaluate image quality, I think in general it's a very difficult task, right? I'm sure we will all come up with all different thoughts or different ideas in terms of what the image quality is. However, how the question is how to measure that, how to quantitatively measure that. So we can all describe, the images, how it should look like, but still we need a kind of benchmark to do that work or that task. So in this area, and we are essentially, we try to evaluate the human's preference in image quality. So if you rather than being provided with a single picture, so if we give you a few images, and especially if we give you a scale, so everybody will be able to do this task very quickly, and you will be able to precision these images on that scale in terms of the image quality. But still, you might wonder, okay, so if how about if myself is different from anybody else, right? So that's very normal. For example, somebody will just precision the images in different places on that scale. However, that's not the issue, right? So that's so basically everything we talk about here is about that relative quality. So the preference of humans, in judging basically, let's say the rankings of the quality, the images. So this is very similar when we evaluate, for example, nowadays the universities, right? If you want to describe, how good this university is doing, it won't give you any measurements quantitatively. But if you do the university's rankings, you will be able to measure that. So in the end, if we ask people to do this task, and in the end we will come up with this so-called mean opinion score. So we use that benchmark. Basically, for any given image, you will be able to quantitatively measure the quality in relative to other images in this context. So this is basically what we do in image quality assessment in this area. Right, just a couple of highlights. And so we've been doing in our lab. So recently we published a image quality assessment model. So this is a deep learning based. And so the contribution we've made in that model was to basically to use adaptive graph attention. If you're familiar with the self-attention mechanisms in deep learning, so this is to enhance basically the feature representations from the transformer-based encoder, right? So we have made that code publicly available. So if you're interested in how this the model works for image quality assessment, so please feel free to go to our website to download the code, and you will be able to implement that model. And also recently we've published a few databases. This is one of the databases I just want to highlight here. So it looks at different same categories in image quality assessment. Right. So that's that's a brief introduction about this area and also the contributions we have made in recent days. So my talk today, I'm going to focus on attention, the saliency modeling. So back in 2011, we started to look at this issue, right? So as you have already seen that in the previous examples. And so when we interact with images, right, we don't look at everywhere, at least we don't look at everywhere equally. So the simple, research question is, back in 2011, so we wrote a paper about, what actually happens. So if you get the ground truth attention map from the human beings, right? So what's the contribution that map will do for the image quality assessment? So we did some study, and you can see, by simply, if you trade this attention map from the eye movements and as a weighting function to weight your distortion measure, so that will give you sometimes 5% in some areas. So that's a significant improvement. However, it will, we always have that, it depends, problem, right? So we started to look at, few challenges in this area, right? So the first thing we really want to answer is, can we actually predict reliably the saliency, right? So the question is, if you have ground truth of my eye movements, can current models actually, mimic that eye movement in terms of saliency? So this is the initial question we really wanted to answer. And the second one is, just suppose you have that saliency information. The question is, how does saliency play a role in your decision making? For example, when you decide image quality, right? So how does that saliency, play a role? So this is the second question we want to answer. And in relation to that, so what's the impact of that, saliency in terms of visual content, for example, the content dependency and distortion types. And recently, we've also looked at, the temporal impact as well. So I'm going to, touch upon for those issues in my talk today. Right. So first of all, I'd like to hopefully to bring everybody on the same page, right? So in terms of the literature in saliency modeling, so essentially we are concerned about where people look, right? As you can see from this picture, to be able to know that, thanks to the current technologies, and we have the eye tracking systems which can help you to get that information, right? So this is a little bit background in terms of salience modeling in the computer vision area. Right, as I said before, this is an important mechanism in our vision system. So if we don't have that, just you can imagine that we can't even move around, because every second there's so much information coming to your eye, and if you don't have the attention to help you to select the most relevant information, you won't be able to process those complicated information. Right. So a little bit, fundamental understanding of visual intention in general, right? So there are two fundamental mechanisms which drive, our eye movement, our attention. So the first one is, it's called the bottom up. So this is a salience-driven, task-independent. So we are talking about the free viewing task. And the second is, the top-down, a more task-independent control in your visual system. Right. So when we talk about saliency, so this is really about the task-independent mechanism of your attention system. Right. So in computer vision, when people talk about salience modeling, it's really about building a computation model which can mimic this bottom-up attention. So it's free-looking without task involved. Otherwise, you can imagine everybody is different depending on your previous experience and your background. You might look at different regions in that picture. So to collect this, the salience data, really, if you want to use eye tracking system to collect the data, you really have to do, the free looking, especially in the first few seconds. So how people move their eyes, and you will be able to capture that bottom up attention. Right. So hopefully, with this understanding, so everybody is on the same page of saliency modeling. Right. So in 2017, we published this paper, and to actually, so we thought, okay, what actually happens? Because at that time, the publicly available databases usually they don't, it's still that might be the case for now. They don't give you all the data you needed. So we started to collect the eye movement data in our lab. We as you can see from those 3 pictures, the visualizations, if you're given that in picture, we ask, in this case, 20 people to look at that picture, and we actually create this so-called saliency map. So saliency map is more about the probability distribution. So where in that picture humans are more likely to focus their attention. Right. So we also answered a very important question in this area. So when you try to collect eye fixations from humans, how many participants do you really need, right? If you can easily think of if you only have 2 people, right? If they really behave differently, so that will give you a salience map, which is different than you collect the salience from the other group of 2 people, right? So how many people do we really need? So as you can see from that graph, the salience map start to become saturated when you have 10 people's fixations. So that means adding more participants to your salience map won't change the distribution significantly. So make sure in the future, if you collect fixations to generate the salience map, you have enough number of participants. So that's the one of the studies we carried out at that time. So in terms of saliency prediction, right? So we should be aware of the other important area in computer vision, which is called salience object detection. As you can see, this is really about the same segmentation. This has nothing to do with that, probability distribution of my eye movement. Just kind of, a clarification between these 2 different areas. Right. So now I'm going to go through very quickly, especially for those of you who are interested in salience modeling literature. So again, this is about modeling the bottom-up saliency, the free-looking and the gaze patterns. Right. So in 1998, so E.G. published this very famous paper. So this is one of the early models to predict where people look in images. It's a very interesting paper. So basically, they also had a few follow-up, important publications in this area. So the question they wanted to answer was, what are the cues, right? So what are cues that attract your attention to some locations in that image rather than the other regions? So very standard, classic image processing work, as you can see from the diagram, right? So if you have the input image, so they use, so basically a bunch of filters to extract, relevant features, and you can see the color, intensity, orientations. Those are the basic, image, low-level image features. So in the middle of a graph, it's very interesting if you are very keen to understand, salience modeling. So I enjoyed quite a lot, reading these papers regarding, once you have those, low-level features, how to combine them, in order to generate the single salience map in the end. So essentially, ET published, a few papers on that. As you can see, I'm going to, show you, the challenges are. So if you rely on your image processing techniques to do that, but this is, this is the initial work you can see. And very briefly, so this is, once you have as you can see from the left part of the slides, and once you have, generated that salience map, how actually can you use that map to guide your eye movement? So this is kind of to mimic the human visual system. And so suppose you have that salience map in your brain, immediately, generated once the visual information comes into your eye. Right, now the next step is how do you actually use that map to move your eyes. So they've actually incorporated some vision inspired models, and as you can see from the previous slides, the winner take all and inhibition of return. So these two important vision inspired mechanisms. Actually, it's quite straightforward when you look at the graph, right? So first of all, you pick up the most salient region in your picture based on that salience map, right? So as you can see, the black hole there. Then next, if you want to move your eyes and you just try to find the next most salient part, and you are not allowed to return to that black hole in that image, so that will force your eye movement in this image. So this is a important work in the literature. So actually, the research developed significantly after especially after 2012. When MIT published the benchmark data set. So as you can see from that graph, right, so MIT actually they collected 300 images, and for each image, they asked people to basically look at each of these images freely, and they collected the fixations and generated the salience maps. Right. So based on that benchmark, so people in computer vision area, people started to to develop salience models, and the good news is people can compare their salience models. So I just want to highlight, as I have already mentioned, the classic model developed by E.T. Perhaps if you contrast that salience map generated by each model, that's in the middle of this graph, or if you contrast that with the ground truth fixations. So can you understand why that happened? So suppose the areas you are interested in looking at, and if you compare that to ET's model, do you think that makes sense? Yeah, indeed. So we're more sensitive to text information and the faces. But if you look at ET's models, basically they just capture the contrast, right? Obviously, for example, the top picture, the brightest area is indeed they capture the brightest area. It's contrast, but that doesn't give you a good prediction in terms of human fixations. Yeah, so you can you can check more examples. For example, some easy cases for humans, and obviously, if you only have that simple contrast detection, you will be able to capture that saliency map. However, again, human faces and text. So those are the challenges, in this area. Right. So people started to look at, what happens if we try to learn a model of saliency, using machine learning. So for the early, models in this area, so people try to apply, the traditional machine learning algorithms, for example, the feature engineering work. Especially in the past five or 10 years, right? So deep learning becomes very popular, and the question is, can we do better work with deep learning? So I'm going to skip this. And so if you're interested in the available databases and for saliency prediction, so they are available online. Right. You can from this graph you can immediately see different results. If you use traditional models like EG's model, what happens? What the difference is between that model's output and the ground truth. And deep learning based models obviously can give you a better result in that situation. So many deep learning based models have been published in the past 5 or 10 years. So yeah, I'm going to just very quickly to go through the popular architectures in this area. So the 2016 paper, right, is quite straightforward, CNN-based architecture. So I think that the contribution they made was to combine multi-layer, multi-level features, which makes sense, right? So for salience prediction, if you think about the higher level features or lower level features, you'd better do a better job to combine to get good balance between those, and in order to predict saliency. So the GAN-based model published in 2017, so which also makes sense, right? So if you look at how to fool your discriminator by generating a better salience model, salience map, in relation to the ground truth, in the end, your generator will hopefully produce a good saliency map. And the long short-term memory, so very important mechanism, so very popular, and also it made a successful case in salience prediction as well. So that was published in 2018, and all these models are available online, and you can download and test these models. Right, so this is a recent one. And so I'm going to move to our work so our contribution in this area. So so after that paper was published in 2017, so everyone knows the attention is all you need. That has been successfully applied for natural language processing, and it has already been successfully applied in vision as well, right? So the idea is we can treat an image as a sequence of patches, and we can assign the different weights to different weights of importance to different parts of your sequence. So that's the important concept of the transformers, right? So the idea is to try to capture the long-range dependencies and contextual information from your feature representations. From all the popular architectures I have just introduced very briefly, so basically the one thing all this model trying to do to actually combine the multi-scale features in order to get the right balance for that prediction task. So right, so this seems to be a very elegant solution, in terms of capturing long-range dependencies. So we applied that, idea in 2022. And so again, the code is publicly available, and feel free to download the code. And so the idea was to integrate the transformers and to the CNN architecture, and especially this was a the 2022 version, but now we're working on updating this architecture, especially with the VIT, the vision transformer, the version at the moment, so we can easily update. But the idea stays the same, right? So how to use transformers to enhance your feature representation. Right, so we submit this to the MIT benchmark, and as you can see, in terms of the perception-based metrics, so of course there are few metrics to evaluate your saliency prediction. So some of these metrics are more applicable for the object detection, for example, like the AUC family, right? So those metrics are good for the object detection. But if you really want to, to check the perceptual difference between your output and the salience maps, so you have to rely on this perception-based metrics. So now our model is ranked #1 on MIT benchmark. Of course, there are some green models which are, if you are interested in they are called probabilistic models, which means they don't generate, they don't immediately generate the final output. They generate the intermediate features, right? But you optimize those features for individual, metrics. So evaluation metrics. In that case, there's no guaranteeing, that this is a general model which can just one image input, the salience output. So those are different than the traditional salience models. Right. So this is the benchmark, and you can have a look at visually you can compare the difference between the model output and the ground truth, especially if you look at the middle picture, right? The basically two human faces, and most of models they try to capture just one, focused on one face rather than two faces. So the few challenges for existing models there, but we improved that situation with especially with the transformer-based encoding. Right. So I still have 3 slides. So I'm going to just go through the recent work, the recent projects we've been involved in. Right. So yeah, very quickly. So SSPnet, right? So this is very interesting, especially if you are working on distortions, right? So what happens if distortions occur in your picture? So how does that impact your eye movement? So this is, as you can see from the illustration, the saliency will actually shift away from the original places, and in that original picture. So that's kind of a distraction created by the distortion. So if you want to, so in this work we try to basically build a model to predict that saliency shift. So that means if you have your original picture, if you have your distorted picture, so the output will give you the areas where your saliency, your attention will shift to. So right, so in that case, if you know those regions, you can use that information to optimize your image coding or enhancement algorithms, because people will be distracted by your distortions, obviously depending on the strength or type of distortions as well. Right, so we've also made a plus version of our salience model, which is called Transnet Plus. So the question is, again, in the context of image quality assessment, right? So we can potentially apply different types of distortions or different levels of distortions, but what happens, the question is, can we predict accurately the saliency maps, right? We know that if you give different images, slightly distorted images to the original, so the saliency maps will be different. So the question is, can we actually build a model to predict that saliency map from any given distorted image? So this is a module we developed. Essentially, the idea was to basically enable capturing the salience features in that salience prediction model, right? Sorry, the image quality features. So basically, how to combine the image quality features and the saliency prediction representations. And as you can see, so this is in that part we ask the network to learn IQA score and to make sure the combined feature also contains the distortion related features, right? So this is so last one, right? So if you're interested in I think in this morning Andy brought up this idea of so how about the defects or the artifacts whenever they occur in your video viewing experience. As you can see from those from two sequences, the reference sequence and the distorted sequence. If you compare the salience maps, it's very interesting, over time, basically how much you are distracted will depend on the time. As you can see in the beginning, right? Even though there are distortions, you are actually not distracted too much. If you compare that salience map to the original salience map, that might be the central bias behavior of human beings, because we always focus our attention in the center of the picture the first time you interact with the image, right? So that might explain in the beginning of viewing, even though the same distortions applied, so you are not very much distracted. But over time, especially if you look at the middle of your viewing, right? So there's a significant level of distraction, right? If you compare the salience maps. And towards the end of your viewing, your attention comes back, right? So because perhaps you've learned, okay, so there are distortions going on, so I'm not going to be bothered by those distortions. I'm going to focus on the content again. So that's why slightly, you come back and to the salient object, for example. So this is the work we've recently published in conference, and I think the more details will come up in our journals. The journal is still under review. But the work we want to do is, can we construct a model to mimic that behavior and what we call the salience shift behaviors, and can we incorporate that in enhancement algorithms or image quality assessment